Hello students, welcome to another tutorial on mechanical properties of matter. In this video, we'll look at a question I left you guys with some time back. So this question just works on the basic concepts that we did back. So it just works on Young's modulus, stress and strain. Now, before we go anywhere really, I hope you've tried to work it out, you attempted it, and then you use the hint I gave in the previous video to work it out. If you have done all that, we can dive right into the calculations and see what you expected to do. Now, before we go anywhere, here we're dealing with a composite wire. So then what is a composite wire and how do we treat it really? So that's the first thing that we're going to look at, a composite wire. Well, a composite wire is just a wire that is made out of two different materials. So one side can be one type of material, it can be copper, it can be steel or brass. And then the other side, it can be a different material. So now, one other thing that you have to take note, or just keep in mind, is the two wires do not necessarily have to be of the same cross-sectional area A. So you can say maybe one has cross-sectional area A1 and the other has cross-sectional area A2. But sometimes you can be told that the cross-sectional area is the same. Sometimes the cross-sectional area is going to be different. But regardless of what the cross-sectional area is, how you handle it is still the same. Now, in this case, I've just indicated that the cross-sectional areas are different, but of course, if they're going to be the same, then the problem doesn't really change. Now, what is true about this type of a wire? Well, we're saying at this particular point, the two are kind of attached. So if you have L, let's say this side you have wire A, or you can say wire X, and then this side you have wire L. So if this is the initial length of wire X, and this is the initial length of wire Y, and then this wire X has a Young's modulus wire X, and this has a Young's modulus wire Y. Now let's look at one wire first of all. Let's say this is the length of the wire, this side. Well, you guys should recall from your studies previously that different materials will stretch differently under the same force, of course. Now, what determines how they stretch, of course, it's all entirely up to the material you're dealing with. Some materials will stretch more when exposed to a force, while some materials will stretch less when exposed to the same force. That's one thing that you have to keep in mind. So wire X might stretch to some point. We'll call this change in L for X. But of course, here we're saying the two wires are under the influence of the same force. So if, let's say, at the far end, you exert a force, let's say F in this direction, the wire X will experience the same force in the same direction. The wire Y will also experience the same force in that direction. But then how they stretch will be different. So for wire X, the change in that length is going to be changing Lx. But then for wire L, not wire L, the wire Y, what is going to happen is it's going to stretch as well, but not really the same way as that the other wire stretches. Maybe for this one, the stretch might not be, you can even say, it might not really stretch that much. So change in L for wire Y. So it might stretch, but just a little bit. But then these two wires are attached. Now, if they are attached, what this implies is if we were given the full stretch of the entire material, let's say after applying the force, the whole material now, which was initially at a length, let's say L, it has stretched to some, by some degree, let's call that change in L. Now, what you should keep in mind is to get the full stretch of the entire wire, you kind of have to add how the wire X stretched and also how the wire Y was stretched. These two will be the ones which combine to give you the full stretch of both wires. Now, what do we mean? We mean that the change in length for the full wire, the composite wire, will be given by the change in length of the wire X plus the change in length for the wire Y. Okay, now this is the key equation that I left you guys with in the previous video. In the previous video, I asked you guys that you use this trick to get what you're looking for. Now, how does this really work? Because here, all we're looking at are the changes in length. We don't really have the the force that the question we want to work out has. Well, from here, really, it depends on what you're looking for. For the question, what they want us to find, the question that we're going to work out with, what they want us to find is the load F. Now, it can be that they want you to find something else, but from this point, after you have this equation, the next key thing that you have to remember is that relationship for Young's modulus to stress and strain. So you recall that Young's modulus is equals to stress over strain. Of course, if you play around with this, you should recall that this reduces to give you force over L divided by the cross-sectional area multiplying the change in length. Now, this is just a general equation for Young's modulus. Now, if I make change in L the subject of the formula, then we can see that the change in length of any material or of a wire, of course, just any material really, will be given by the force, the length, then this is going to be divided by the cross-sectional area, and then apart from this, the Young's modulus of that particular material. Now, with this in mind, we can easily evaluate what the change in length of each particular wire is, substitute it to where it has to be, and then use, of course, the respective terms. If I'm working for X, I'll use the cross-sectional area for X, I'll use the initial length for X, I'll use the Young's modulus for X. If I want to calculate the change in length for the wire Y, I'll use the cross-sectional area for the wire Y, the length initial for the wire Y, and the Young's modulus for the wire Y. And if it's something else that they wanted me to find, of course, and then I was not given the full stretch of the wire, I could have easily done the same thing, get this and substitute it there, and then of course work out whatever they want us to get. But of course, this is the key equation that we have to work with. So let's label it equation 1. Now, with that in mind, how do we actually work out the composite wire problem? So we go back to our question. Now let's extract what we've been given here. Well, let's start with what materials do we have here? We have two materials. This wire is made out of copper. So for copper, what we're told is that copper has length, initial length, L. For copper, I'll put subscript C. This is 2.2 and it is already in meters. So I'll just write it like that. Now, notice the first statement there, a composite wire of 3 millimeter uniform diameter. So if the diameter is uniform, it means that in this case, the cross-sectional area for copper is going to be equivalent to the cross-sectional area for steel. So this is very important in this question. Just take note of that. It's going to, it doesn't really matter even if they are different, we could have easily calculated what A1 is and what A2 is, and then of course use them where we have to use them. So of course, to get the area, since what we're given is the common diameter, so we're given the diameter as 3 millimeters. So you can easily convert this to radius. Just half the diameter gives us the radius, which is 1.5 millimeters. And then next thing to meters, just this becomes 1.5 by 10 to the power -3 meters. So this is common for steel and for copper. So the cross-sectional area for copper, since this is a wire, of course, the cross-sectional area is circular. So this is going to be pi r for copper, of course, which is the same, so just write r squared. And then, of course, the r is 1.5 by 10 to the power -3. So this is what we have for the cross-sectional area. The next that we have to do, of course, what else are we given? For copper, we're also given the Young's modulus for copper right towards the far end. The Young's modulus for copper, YC, is given as 1.1 by 10 to the power 11 newtons per meter squared. Is there anything else for copper that we've been given? Of course, that's the only thing that we've been given. So the next thing now, we go to steel. What have we been told about steel? I'll put that right back. So for steel, first of all, I'm given the initial length for steel. So I'll use L subscript S to mean steel, initial length for steel. So the length of steel is given first of all as 1.6. So 1.6 meters. This is already in meters, with no need for conversion. The cross-sectional area for steel. So this is a steel. So remember, it's the same thing, same cross-sectional area since the diameter is the same. So I'll just get what we derived for copper and then just place it here. 1.5 by 10 to the power negative 3. This is the cross-sectional area. Of course, since I already converted that radius to meters, the units are going to be standard. So this is going to be meter squared. This is also going to be meter squared. And then next up, we have the Young's modulus for copper, which is going to be, not copper, sorry, this is steel. The Young's modulus for steel is given as 2.0 times 10 to the power 11. So this is newtons per meter squared. And just write that as a Pascal. It's the same unit, just since I don't have space, I can write it like that. Now, next thing, of course, these two wires, they're under the influence of the same force as we described earlier on. So I can just write FF. This is the force that we want to find. It's the same force, really. Now, what do? Well, we have to remember that change in L is equal to change in L for copper plus change in L for steel. Now, the full change in L for the whole wire is given in the question as 0.7 millimeters. So the whole material changes by 0.7 millimeters. So this is given up to 3 significant figures. So this becomes 0.7 by 10 to the power negative 3 when you convert it to meters. Now, with this in mind, so our equation, this equation becomes 0.7 by 10 to the power negative 3 is equal to change in LC plus change in LS. Now, let's hold on to this as our equation 1. Now, it's up to you here. You can substitute what we had for the expression for change in length. So you can substitute here, can substitute this already for the respective wires, so that you get the changes right away and work out a long equation, or you can work them out separately. So you can say the change in length for copper is equal to our expression. So that is the force, which is common for both copper and steel, the length for copper divided by the cross-sectional area, which is the same whether copper or steel, multiplying the Young's modulus for copper. Working out this, when you perform your substitution, the only thing you don't know is the force, but this is multiplying the length of copper, initial length. So copper initially had a length of 2.2 meters. So we're dividing this by the cross-sectional area, which is, so this, if you, of course, we left it in, let's see, where is that? Okay, so that is pi. And then this was, let's go back, that's 1.5 by 10 to the negative 3, 1.5 by 10 to the negative 3. So this is like that. The whole thing, this is just cross-sectional area. So don't forget, this radius is squared. So pi r squared. So the Young's modulus, on the other hand, for copper, this is given as 1.1 by 10 to the power 11. So if you work out this, you should be able to get the change in length. So here, just simplifying the denominator, dividing it into 2.2, you should have 0.00000, and then 2829F. Okay, so let's hold on to this as our second equation. Yeah, we can hold on to that. So next up, we go to the change in length for steel. It's the same thing. We have F, it's the same force in each case, but now the initial length of the wire, we're just looking at the section for steel. And then this is divided by the cross-sectional area. In this case, it's the same cross-sectional area for steel and for copper, so I'm just writing A. But if you're dealing with a question where the cross-sectional areas are different, the value you substitute will have to be different here to when you're dealing with steel down here. So of course, the Young's modulus here is for steel. And what you get here is F multiplying the length, the initial length for For steel, that's 1.6 meters divided by the cross-sectional area. It's the same cross-sectional area again. That's 1.5 by 10 to the power negative 3, and this is squared. So this is cross-sectional area multiplying the Young's modulus for steel, which is 2.0 by 10 to the power 11. Now the units are all standard that I'm using here, so I'm not writing them here. I know the final answer will have the correct unit. So if you simplify all this, simplify the denominator, divide it into 1.6, what you're going to get is going to be changing L for steel is equal to 0.00000, and then now you have 1132F. So now this is going to be our third equation. So from here you can substitute equations 2 and 3 into equation 1. So remember what our equation 1 was? This one. So we're going to substitute equations 2 and 3 into this one. Equation 2 gives us the change in length for copper. Equation 2 gives us the change in length for steel. So we can substitute those. So what we now have is the change in length. Okay, we can just go right ahead. So what we now have is going to be 0.7 by 10 to the power negative 3. This will be equal to 0.00000, and then here we have 2829F. So this is the change in length for copper, plus for steel, what we have is too many zeros. Yeah, 5 of them. And then now I have 1132F. So the right hand side is common. We can add them, we can simplify. So the left hand side remains the same. But the right hand side can simplify, and it gives us 0. Then we have 3961F. So from here, we want to work out what F is. So we'll divide both sides by its coefficient. And then we see that what you're going to have is 0.7 by 10 to the negative 3 divided by this gives us what F is. So when you simplify the left-hand side, what you're going to get is 176.733. Yeah, that's, and then the next thing is a 79593, and then this is what gives us F. So now you can switch this so that you start with F. So this is now 17. So depending on the level of accuracy that you want, but the standard you can work with is 3 significant figures. But of course, sometimes you can try to look at the question and the type of the significant figures that the question was phrased in terms of the values that you are given. But in this case, I'll stick to the standard of using 3 significant figures. So I'll round off my final answer to write it to 3 significant figures. So this becomes 177 newtons. So of course, I've just rounded off the last value, so that I have 177 newton. But of course, this could have easily could have also written it as 176.7 newtons. So this is the load that they wanted. I hope you guys were able to follow through, and I hope you understand how to approach it now. So just to help you guys practice, there is another question that you can look at. I'm sure most of you might have seen this question before, but I'll leave this question for you guys to try. It's the similar approach we had. Everything is basically the same. The difference is the previous question we had copper and steel. In this question we have copper and iron. Another difference here is that the cross-sectional areas of the 2 wires are different. But then the question, of course, does specify what these areas are. One is given there, and then the other one is given down here. So I hope you guys will be able to use the methods that we have worked out to calculate or to work out this question. So yeah, you guys can try this question out. Let me hear your reactions in the comment section. Was my description of the previous question helpful for you guys to be able to work this one out? If you still struggled, if you're not clear anywhere, Where did you find your problems when you tried to work this question out? Let me hear all that in the comment section. I'll be happy to read your reactions, you guys. If you found the video helpful, you can like the video. Otherwise, in the next video, we're going to go back to fluids at rest, and then we're going to introduce the concepts of Archimedes' principle. And then we're also going to use that, that principle to work out this question. So I hope you guys will also be able to try out this question. And then we'll see you guys in the next video. This was your tutor.